Welcome back to our last video over general equilibrium. Just wanting to wrap up with some other things we can do with K, the equilibrium constant. We actually have already seen some of these and you have just really never known it, or I've been telling you we'll deal with that later. And that is we can do delta G, that is Gibbs energy. So Gibbs energy is the energy that happens when we change all the reactants into only products. But in an equilibrium, we still have some reactants left over. So we can actually account for the difference. What would the G be if we could convert all of the reactants into the products when we can? Well, here's our conversion. And I want to point out a couple things about this. I want to point out that we have the Kelvin temperature like you're used to. We have R as, now R is a gas constant, but we're working with G in joules, probably kilojoules. So you want the R measured in joules. Pick from, of the three R's on the formula sheet, pick the one with joules in it. And now we take the natural log of K. And K is, of course, concentration of products divided by concentration of reactants to some exponent powers from the equation. That is K. Now, on the formula sheet, this is what it looks like. Okay? But we can use Kc, Kp, those are just special Ks. We can also use Q there. We could absolutely do a negative RT ln of Q if we don't know we're at equilibrium. So all of those are possible. Keep that in mind. Although this one formula's on the chart, you could substitute any of those in for K. Now let's talk about how this would work real fast. Okay. We would have some, concentration products, reactants. If the reaction went really far in the forward direction before reaching equilibrium, K would be large. A large K, when we take the natural log of that, is going to be positive. When we negatize that positive, G ends up negative, and that would be a spontaneous reaction. Well, that would make sense. If it went far in this direction, if it went a lot of reactants used up to make a lot of products, so there's just a itty-bitty tiny amount of reactants left, we would expect it to be spontaneous. That sounds like a spontaneous reaction to me. What if it was not that? What if it was not a spontaneous reaction? In other words, what if just a little bit of reactants made products and a whole lot more products made reactants? Well, K itself would be a number less than 1. The natural log of a number less than 1 is a negative, and when we subtract that negative, that makes delta G positive, and we would say it's not spontaneous. So what we could clearly do is say if I have reactant A and B, forming reactant C and D. Okay. And I start with 0 of this and 0 of that, and I start with a whole lot of this, I don't know, 100 molarity of that and 100 molarity of that. I'm just throwing out random numbers, that's a 100. Obviously, the forward reaction is not going to be spontaneous, so we would expect for the forward reaction, we would expect a positive G. Now, of course, the reverse reaction would be the inverse of K. So if you go in reverse, you flip your K, and inverse of a less than 1 is a greater than 1, and then it's suddenly this term is positive and delta G is negative, and it would go. So we could use delta G to evaluate how spontaneous a forward or reverse reaction is in that equilibrium situation. Okay, and let's answer, if you haven't already, why would delta G reaction be less than if there are still some reactants left over? Well, because again, the energy is energy to convert all reactants to only products, and there's a little left over, so little reactants left over, so we're not going to release all the energy that's possible or absorb all the energy that's possible in an equilibrium situation. So here's the way that we account for that. Okay, we also have had this one on the formula sheets. We have not used this one. Why have we not used this one? Because we have not dealt with equilibrium topics yet. And check out what this one's going to do for us. This one's going to do for us how we take a standard Gibbs energy, that's at standard temperature and pressure, 25 degrees Celsius, and convert it to a G at any other temperature. The way we account for the temperature change is with putting the new temperature in there. Now, R is still going to be the one with the joules from your formula sheet. And then we're going to have our Q, and our Q is going to be concentration of products over concentration of reactants. Okay. This must be a Q. Why must it be a Q? This must be a Q because what have I messed with? I've messed with temperature. This standard is 25 degrees Celsius. This is not standard. This is at a different temperature. It's got to be a Q because changing temperature changes the value of K. All right. Now, for both of these, again, and this would just be a plug-in chug situation. You just plug in the numbers you're given, solve for what you're looking for. It is a great way to get your new G when given an old G. Not that that is going to be common. This reaction, this equation is quite common. So nice and easy. 1, 2, 3, 4 variables. You'll plug in 3, solve for the 4th. It should be no big deal. And R is not even technically a variable since it's on your blue sheet, or sorry, your formula chart. So there you go. Okay. Now, I've said this both times. R is, in your formula chart, the ones that are, the blue copies that we use on tests and quizzes, you want the one in joules. Be sure you use the one in joules. However, G is typically measured in kilojoules. So be sure your units match, not just joules to kilojoules, but be sure on both sides of the equal sign you end up with either both joules or both kilojoules. Now, if you know one side and you're calculating the other, easy enough. But if you're given like this and this and you want the temperature, be sure that your R joules or kilojoules match your G joules or kilojoules. Be sure that all matches. It really does you a favor to write the label on every number you plug into an equation so you can be sure the ones that need a match, match, and the ones that need to cancel, cancel, and all of that. It's there for your good. Do it. Okay. And we have the Nernst equation. And again, the Nernst equation, though not actually on your blue sheet, is super helpful. Now, when I told you this earlier, it did not look like this. Instead of the Q, I said concentration of product ion divided by concentration of reactant ion. So, is that a lie? Did I lie to you when I said that? Well, no, because what did our equations look like? There was something that was a solid added to something that was an ion, and, arrow, and then something that was a solid and something that was an ion. And what do we not put? What do we never put into a K or a Q? What two things should we never include in a K or a Q? Pure solids, pure liquids. And on each side of the arrow, we had a pure solid. So when I was telling you, you take product ion divided by reactant ion, I was telling you, you take Q. That's exactly what I was telling you, because that's what Q will end up to be. Prove it to yourself. If you don't understand what I was showing, then go write an electrochem reaction, and then write a Q for that electrochem reaction, remembering not to add in solids or liquids, and you'll see suddenly you get product ion over reactant ion. It really does come out that way, nice and easy. So I did not lie to you. I just didn't want to discuss what K or Q was. Why should this be Q in the equation? And it really should be Q. And it is not on our formula sheet, so you don't even really have to worry about calculating it, but I am pointing this out. Why should it be Q? Well, the only reason this electrochemical reaction goes is because it's not at equilibrium. So I have my reaction, my two beakers, I have my electrodes connected to a wire to a voltmeter, I have my salt bridge. Okay, we know the setup. I started off. I throw a switch and my meter reads, let's say, 1 volt. What happens over time? My 1 volt becomes 0.9 volts. Then it becomes 0.8 volts. And then it becomes 0.7 volts. So over time, as the amount of reactant ion decreases and the amount of product ion increases, I start subtracting away more and more from my E cell. Okay? And it just keeps going and going and going. We have batteries that do this. I mean, this is what batteries do. It starts as a 1.5 volt, a AA, but it doesn't stay permanently that. As you use it, it starts getting slower, slower, slower. And it's really a shame that no one has a Walkman anymore. But if you've ever listened to a cassette tape player as the battery runs out, it's really, your batteries are running out when, someone starts talking slow. And everyone knew that meant your batteries were running out. What's that actually mean? That means your batteries are reaching equilibrium. Once equilibrium has reached, there is no voltage because there's no difference in the rates of reaction. There's no more push for those electrons to go one direction because they start going in both directions at the same rate, which actually means nothing ends up moving. That's a physics topic, and we're going to discuss that in physics. But if we had a push of electrons from both sides, equal amounts, nothing's actually going to end up moving. So at equilibrium, your batteries are dead. So we cannot ever use a K when we deal with electrochemistry because your answer would be 0 at equilibrium. There is no voltage at equilibrium. Should always be a Q. Again, this equation is not on your formula chart. It's super great to explain all of this. I wish it was on your formula chart so you could use it without memorizing to explain all of this. But they want you to say about Q is less than K, Q is greater than K. And the whole point of an electrochemical reaction is that you start off between Q and K, that Q is less than K. And if you're building a battery well, your Q is way less than K. And so it has to go in the forward reaction. That's going to give you your amperage and your voltage. It has to go in that forward reaction for a long time before it reaches K. When Q equals K, your batteries are dead, and we say you have to throw them out or hopefully recycle them like a good steward would. Okay, take care of the earth, recycle your batteries. But that is what happens. So electrochem happens in this whole region where Q and K are not equal. And so anything you talk about with equilibrium and electrochemistry, reference Q all the time, not necessarily K. Okay, one last thing. We have mentioned how equilibrium constant changes with temperature change. And we've already used Le Chatelier's to discuss why how we can predict the new K versus the old K, the size of it. Well, what if we don't want to just predict? What if we actually want a number? What is the new K if I raise the temperature by 259.3 degrees? Okay. Well, Mr. Van Hoff has helped us out with this. We can use the Van Hoff equation, and you'll notice it looks similar to other Van Hoff equations. We can use the Van Hoff equation to calculate the K. That is the equilibrium constant. So there's the equilibrium constant at temperature 1 and what it is at the new temperature 2 and what was the old temperature 1 and the new temperature 2. And we do have an enthalpy thing going on there. We do have an ideal gas constant R, which would still be in joules. Okay. This is not on your formula chart. It is quite a bit of math for very little chemistry, so I really do understand why this is not there. There's really no need to calculate this. Just wanted to show you that we do have equations that can do this for us. It is something that a lot of people have spent their life work on, like Mr. Van Hoff, trying to figure out what are these relationships mathematically. And it really is rather elegant that we can predict and we can actually calculate something so seemingly so not connected between equilibrium and enthalpy and temperatures, and yet we with a 1, 2, 3, 4, 5, 6 variable equation we can connect it all. So the fact that the universe works out so eloquently is really nice for us, and really all of science, kind of based on this fact that there seems to be some really nice, not too difficult ways to connect all of our phenomenon in science. And chemistry loves that you can connect one field of chemistry to another. So they love these kind of questions where you have to talk about it's not at equilibrium, it's working to get at equilibrium, and the cell voltage is going to drop until you get to equilibrium and then zero. They love to talk about, I went the wrong way, how G is connected to K or Q or whatever. They love this equation for that. It's a great way to connect what we've talked about already from different topics of the book into one question, one like long question on the test. They love to ask those type of questions. I would fully expect that you'll have to answer a question like that this year. So lots of connections to be made. These are not trivial connections. The good news is the equations and the math involved in the equations is rather trivial. I mean, it's rather simple algebra. So good news for us, simple algebra for the most part, but you have to remember, and I don't know why, come May, students seem to forget that, yes, I did show you how you connect from Gibbs energy to equilibrium. There's a nice 4-variable equation for that. Here it is. G equals negative RT ln of K, or negative rat link is what a lot of people say there. We have equations for that. They're on your formula chart. If they expect you to convert from one topic to another, I'm going to guarantee you there is an equation on your formula chart to do it. So take the 30 seconds to a minute it might take on your formula chart and hunt it down. It'll be well worth the points in the end to do that. Hopefully you're like, oh, I know there is that equation, let's find it, and then it takes 10 seconds. But if you're sitting there and you're like, well, I don't know, is Gibbs energy related to equilibrium at all? At least bother to look it up. Okay, that's all I have to say about general equilibrium. Now, this is the start of our entire semester long, and by that I mean maybe 6 to 8 weeks long look at equilibrium, and then we're going to stop and do review for the test because we're done. But this has been general equilibrium. Now we're going to get to some special equilibriums later on. We're going to move into ion product equilibrium, or solubility product equilibrium is what most people call that. That is KSP. After that, we'll move into Ka, equilibrium constant for acids, Kb's, equilibrium constant for bases, and we even will throw in a discussion of buffers, because that is of importance as well. So it really is downhill from here, and it's all equilibrium from here on out. So it is super important to be sure you grasp the idea of general equilibrium so we can build on this. This is foundational for the next several months in AP Chemistry. And this is equilibrium in general. All of those equilibriums I just talked about are a huge portion of the test in both the multiple choice and free response. So big deal. Put in the effort now. The test is coming in a matter of months. It's going to be here before you know it. Put in the effort now. I will get you there if you'll put in the effort now to stay with me. So good luck on your practice. We're going to do lots of practice with K. We're going to continue to practice with K. You'll know all about all the special Ks by the time we're done. And hopefully it's a very good day for you come the test in May. Good luck.